Welcome to the video lesson on VSEPR theory. Now, before we actually talk about this VSEPR theory, I wanted you to realize having this lesson in video format allows you to move through this lesson at your own pace. It also allows you an opportunity to review this lesson at any time if you need to do so. And with VSEPR theory in particular, it does help to have some good visuals, so I'm hoping that this video will provide that for you. Now, before we begin, you will need the handout provided in class. This will be your fill-in-the-blank note as you work your way through the video. If you need another copy of this handout, you can find it in D2L under Unit 1 and in the handout folder. Now let's get started on our lesson. VSEPR theory was developed strictly to have a method to predict molecular shapes, especially those more complex shapes with many bonds. And really, that's all it does. But it predicts these shapes extremely well. Now, VSEPR is actually an acronym for valence shell electron pair repulsion. Now, as that name suggests, this theory states that pairs of electrons will arrange themselves around an atom such that their repulsions against each other are minimized. In other words, the electron pairs are moving as far apart from each other as possible around that central atom. As they do so, the pairs of electrons basically define the shape of the molecule. Now, this theory uses all the electron pairs, whether they are bonded or not. Now remember, a non-bonded pair of electrons are also called a lone pair of electrons. Even though these lone pairs are not part of the bonding, they still take up space and will therefore still help to define the molecular shape. Now, before we start going through our examples, I want to show you a website that I'm going to use during this video. It is a simulation that can give you the 3D shapes of any molecule. I have posted a link to this site on D2L, so if you wish to check it out, then you too can form and move these molecules around yourself. I think it is a pretty cool chemistry site, so let me show you what it can do. Okay, so when you open the site, the front page will give you two choices. You can either look at shapes of real molecules, like this water molecule here, or you could decide to go and make your own molecule using just general atoms, and that's what I want to do. So I'm going to click over here. Now on the next page, you will see there is a molecule already in place. On the right hand side, you will see all the controls for making and disassembling your molecule. Now I want to remove those bonds because I want to start fresh. So all I have now is my central atom. Now the plan for building my molecule is going to come from the Lewis diagrams. Now let's say our Lewis diagram says our molecule has two single bonds and a lone pair. So I'm going to add that to the central atom. Now you will notice that as soon as I add that second bond there and add on that lone pair, that the electrons already are repelling, even in this diagram, and that is basically what VSEPR says. And you will notice that because of the repulsion of the pairs of electrons, it has given a shape to my molecule. Now the other thing this program can do is that you can grab onto your molecule and you can move it around. So you can also see too the repulsions of those pairs of electrons. And if I leave it here, you can see my molecule does have the form of a triangle. Now if I manipulate around a little bit more, maybe in this direction, you can see my molecule too is flat. Well, that's called being in a plane, just like sitting on a sheet of paper. And in fact, we call this planar. Now, because the molecule is also like a triangle, we use the word trigonal. Putting the two together, the shape of this molecule is called trigonal planar. Now, as we go through this lesson, you are going to learn many different shape names which you will have to memorize. You will also learn how to identify the shape names and draw these shapes for any molecule that I give you. And so let's go back to our handout and we'll go through a number of examples. Now we're going to use VSEPR with about 11 different molecules, and for each molecule we will need to keep track of about 9 pieces of information. And so you will see in the middle of your page I have placed a key. Now the number on this key will match the numbers that are in the boxes in your chart down below. So let's go through each one of these items. Now the first one, of course, is the chemical formula for the molecule. Next, in box 2, we are going to draw out the Lewis diagrams, because the Lewis diagram is going to give us the information about how many bonds and lone pairs there are. Boxes 3 through 5 is where we're going to record how many bonding pairs of electrons we have, non-bonding pairs, and then finally, in box number 5, the total pairs of electrons around our central atom. As we have seen with hybridization, the central atom is going to need hybrid orbitals for its bonded and non-bonded pairs of electrons. And since in box number 5 we know how many pairs total of electrons there are around the central atom, we can therefore figure out what the hybridization is, and that will be recorded in box 6. Now for boxes 7 to 8, you will notice that we are naming the molecule now. But what you have to realize, in VSEPR, there is a name for the shape created by the pairs of electrons that are arranged around that central atom, and for box number 8, there is also a name what we call the molecular geometry. Now molecular geometry just concentrates on the atoms of the molecule, and therefore really only the bonding pairs of electrons are going to be included to determine the shape of that molecule. Now this is because you really cannot see a lone pair. Remember, electrons are way too small. Now they will push the other pairs of electrons into shape, but looking at the molecule, you really don't see them in the molecular shape unless there's an atom attached. Therefore, this molecular geometry name can be different from the electron pair arrangement name. Finally, we're going to draw the diagram of this molecular geometry. Now, since some of these molecules are in 3D, we have to learn how chemists handle this in trying to draw a 3D structure. Let's take a look at a molecule with 4 bonds. Notice the bonds on the right side of this molecule. One bond appears to be coming towards you, while the other is going back away from you. Consider now the following symbols to represent this 3D shape. For any bond that's in the plane of the page, use a straight single line. A solid triangle is a bond that is coming towards you, and we use a dashed triangle to represent a bond going back into the page. Therefore, this molecule will look like this on a 2D page. Now, before you start filling in your chart, I want you to realize that my screen is going to look a little different. And that's because I do want to include that molecule building website that we saw earlier. My numbering system for all my boxes, though, is still going to be exactly the same as yours. Now, near the end of the video, I will show you a filled-in chart so that you can make sure you have recorded all the information accurately. But please do not jump to the end and copy. The best learning will happen if you work with me as we go through this lesson. Now, to continue, you will notice that our first set of examples will all be hydrides of the elements that come from the second period of the periodic table. Now, these are just our representative molecules to show you how to determine the molecular shape for any molecule you are going to see. Now, our first molecule, therefore, will be beryllium hydride. So we're going to place that formula in our box number 1. Now, in box number 2, we're going to draw out the Lewis diagram. I want to note, though, that for this example with beryllium and our next example with boron, that these elements are too small to have 8 electrons around them. So you will notice with beryllium, it will only have 4 electrons and therefore 2 bonds, and boron will have 6 electrons and therefore only 3 bonds around the central atom. So now, knowing this information, why don't you pause the video and try this Lewis diagram on your own. It'll be excellent practice, and when you return back, I will give you the correct answer. Okay, now compare your diagram with mine. And if you're having any difficulty with drawing Lewis diagrams, then you need to come in and see me for extra help. Now the next thing we're going to do is use our Lewis diagram and start counting up the pairs of electrons that are bonded, non-bonded, and then finally add them up to give a total pair of electrons. So in box number 3, we need the number of bonding pairs of electrons. Well, you will notice from your Lewis diagram that we have 2. Now in this case, beryllium does not have any non-bonded pairs, so in box number 4 we will place a 0. And then of course the total will just be 2 pairs of electrons. Now I want you to notice we are not counting individual electrons, we are counting pairs of electrons. Now the pairs of electrons are going to help tell us what the hybridization of the central atom is. And so with only 2 pairs of electrons, that means we only need 2 sigma bonds, and therefore only 2 hybrid orbitals, and so our central atom will have a hybridization of sp. Now we come to the name. Remember when I was going through our key for this chart, I stated to you that there are basically 2 names that we have to go through for each molecule. There is the electron arrangement name, and then there's the molecular geometry name. Now the electron pair arrangement name deals with all pairs of electrons bonded or not, while the molecular geometry just considers the bonding pairs of electrons, because that geometry just concentrates on the positions of the actual atoms, and ignores all the lone pairs. But you will notice for this molecule, because there aren't any lone pairs, our electron pair arrangement name and the molecular geometry name is going to be the same. In fact, for the first few examples we are going to see this, and it won't change until we start seeing lone pairs on the central atom. But getting back to the beryllium hydride, I am now going to use the molecular shape simulator where I'm going to build this molecule and we can consider its shape. Looking at the Lewis diagram, we notice that all it has is 2 bonds. So I'm going to now add my 2 bonds here, and there's my molecule. Now you will notice on the screen, even if I do rotate this molecule around, it is pretty linear. And so that's what the name for the electron pair arrangement is. Now, since there's no lone pairs, the molecular geometry name is also called linear. So let's place those names in our chart. When we come to draw this shape, we can do it in the plane of the page, because linear is very much a 2D structure. And I want you to make sure that you do show it as being linear. I know we were really relaxed when it came to the Lewis diagrams, but now that we know what the true shape is, we've got to make sure our diagram shows that. Another piece of information that we are going to consider with each shape is the angle that is created by the bond positions. For example, our beryllium hydride has a bond angle of 180 degrees, as all linear molecules do. Now that finishes our first example. For the rest of the examples, I will show you all of the chemical formulas we will be using in my own chart here. And I want you to stop the video and take some time to complete the Lewis diagrams, and then using the Lewis diagrams, record the bonding pairs of electrons, the lone pairs of electrons, and finally the total pairs of electrons. Looking at the total pairs of electrons, you should also be able to predict what the hybridization is. Just remember, for every sigma bond, you need a hybrid orbital. So copy all the examples down, pause the video, and please complete boxes 1 through to 6. Okay, now compare your answers with mine and make any corrections you need to. Now, if you had any difficulties doing this, then record down your question so that you can ask me in our next class. So let's use this information and move on to naming the shapes of each of our examples. I will first build the molecule in the simulation site, and we will then discuss each compound. Also realize that I'll go quickly through each example, but note you can always pause the video and record the information into your chart at your own pace. Do try, though, to see the pattern that will form as you compare hybridization with electron arrangement name and lone pairs of electrons with molecular geometry. So let's consider our second example now, the BH3, boron hydride. Recall that boron only has 3 bonds due to its small size. And this molecule looks like a triangle in this position, and it is very flat if you move it into this position. We have seen this shape before when I did the demo for this website. This shape is called trigonal planar. Now, since boron does not have any lone pairs, this is also the name for molecular geometry. So you can record this into box 7 and 8. Now, drawing this shape in box 9, you will notice that this shape is planar, and we can easily draw that on a 2D page as follows. The other thing we want to note on this diagram as well is what angle exists between the H, B, and H bonds. As you may recall from math class, the internal angles for a triangle is 120 degrees. And so that is the bond angle in this molecule. Now that finishes our boron hydride molecule. Let's move on now to our methane example. That's CH4. Let's build that shape now. And as we build the shape, you'll notice that it has 4 bonds and no lone pairs. Now we have seen this shape before in class. And hopefully you recall that this shape is a tetrahedral. And I also want you to notice that this always matches a hybridization of sp3. Since carbon has no lone pairs, this will be the electron pair arrangement name and the molecular geometry name. So now record those names in your chart. This time, when it comes to drawing this shape in box 9, the CH4 molecule has 2 bonds in the plane of the page, 1 bond coming out at you, and 1 going back into the page. We therefore need to use the symbols we learned to draw the shape in 3D. Recall that single lines are for the 2 bonds that are in the plane of the page. Then we're going to use a solid triangle for the bond coming out, and a dashed triangle for the one going back into the page. If you carefully draw this such that the 3 bottom hydrogens are below the carbon, you can actually imagine the 3D shape when looking at this diagram. Now finally, if we consider the bond angle in this molecule, all tetrahedral shapes will always give you a bond angle of 109.5 degrees. Moving on now to our ammonia molecule, let's build that with the help from our Lewis diagram. You will notice that this is our first example where the central atom has a lone pair of electrons. This means that our electron pair arrangement name will now be different from our molecular geometry name. So consider the shape first with all pairs of electrons. You can see the shape is tetrahedral once again with a hybridization of sp3, just like our methane. I hope you are noticing a pattern that is starting with the hybridization and the electron pair arrangement name. sp3 and tetrahedral always go together. So record that down in box 7. Now let's make the lone pairs invisible. It is still there though, affecting the position of the other pairs of electrons, but we're going to look at the shape with only the bonding pairs. Now you can see our shape makes this little pyramid. The pyramid, though, does have a triangular base like this. So the molecular geometry name for ammonia is trigonal pyramidal. So record that down in box 8. Now to draw this molecule, you will notice it'll be similar to the methane above. We will place the lone pair at the top, and then there will be 1 bond in the plane of the page, 1 bond coming out at us, and finally 1 bond going back. And since it is a tetrahedral, all bond angles will once again be 109.5 degrees. And there you have it, our ammonia molecule. Water is up next, so let's build that molecule now. This has 2 bonds and 2 lone pairs. Once again, the electron arrangement will be tetrahedral. Remember that sp3 hybridization? Record that in box 7. But when we make the lone pairs invisible, the molecular geometry shape changes to V-shaped. This is also just called a bent shape as well. Now let's record that into box 8. In drawing this molecule, I'm going to keep the 2 bonds in the plane of the page, and I will then overlap the lone pairs to give it sort of a 3D effect, so that our bent water molecule does look a little bit 3D. So what bond angle will occur between the H-OH bonds? I hope you said 109.5 degrees. Now on to hydrogen fluoride. Notice that around the central atom, which is the fluorine, you have 4 pairs of electrons. So in this molecule, the hybridization is sp3, and therefore, as I hope you can guess, the electron arrangement is tetrahedral again. Now making these lone pairs invisible, this molecule becomes linear. Now this is the second time we have seen a linear molecule, but they both came from different electron arrangements. You will see this happening for other shapes as well. Now linear and 180 degrees go hand in hand. Therefore, 180 degrees is the bond angle for this molecule, as it is for all linear molecules. Well, this finishes off our first set of examples that come from the second period of the periodic table. The rest of the examples, you may have realized, are molecules with the extended shell for their central atom. Phosphorus pentachloride is our first molecule of this type, with a hybridization of sp3d. Building it in the simulation program, and using the top atom here as a point for a shape, you can see the molecule resembles a pyramid. This pyramid has a triangular base. Notice though that if I use the bottom atom instead, we can create a second pyramid with the same base, only it's upside down. So this molecule appears to have 2 pyramids with the same trigonal base. Therefore, the electron arrangement name will be trigonal bipyramidal. I hope you will notice that since the central atom phosphorus has no lone pairs, our molecular geometry name is also trigonal bipyramidal. So let's get that recorded in box 7 and 8. Drawing this structure, I am going to keep 3 of the bonds in the plane of the page, which will give us 1 bond on the right here coming at us, and 1 bond going away. Now let's consider the bond angles in this molecule. If we look at the trigonal base only, this looks a lot like our trigonal planar example, and therefore the bonds here create 120 degree angles. But what about the angle created using this top bond or the bottom bond with any of the bonds that are in the triangle? Well, right here in our diagram, you can see that it is in fact 90 degrees. So in this molecule, we actually have 2 different bond angles happening. Going on to our next example, the BRF3, it has 2 lone pairs, which should tell you already that its electronic arrangement name will be different from its molecular geometry name. Its hybridization is sp3d, like our previous example, which therefore matches with an electronic arrangement shape of trigonal bipyramidal, as you see in our 3D representation here. Now let's make the lone pairs invisible, and if I move the molecule like this, what letter does that remind you of? It looks a lot like a capital T to me, and well, that's what its name is. It's called T-shaped. So let's record that into our chart. Now drawing this structure will be similar to our last example, except I'm going to keep the lone pairs in the trigonal base, drawing the overlap with the lone pairs to give it sort of a 3D effect. Now the bond angles will be the same as for PCl5, our last example, But notice that the lone pairs have arranged themselves to be in the 120-degree triangle and not at the top or the bottom, which forces them to be 90 degrees to the other electron pairs. The reason for this is that lone pairs take up more space than bonding pairs do. So you'll always see lone pairs where the angle is greater. Now moving on, I am going to quickly build our next example, which is tellurium tetrachloride. It too has a hybridization of sp3d, which I hope by now you will match with a trigonal bipyramidal electron arrangement name. Now let's make the lone pairs invisible. This molecular geometry is a little bit tricky, and I'm sure the chemists that came up with these names of these shapes were playing with models, because this molecular geometry name for the tellurium tetrachloride is called seesaw. Now drawing it out, the shape is similar to our last two examples and will look like this. Next is sulfur hexafluoride. This molecule has a hybridization of sp3d2. So let's build this molecule. Now if you were to put on faces surrounding this molecule, you'll actually create an 8-sided figure, which is called an octagon. Therefore, our electron arrangement name here is octahedral. Once again, no lone pairs, so the molecular geometry name is also octahedral. To draw this molecule, we will keep the top and bottom bonds in the plane of the page, and then on either side of the central atom, we will have one bond coming towards us and one going away. You will notice that all bond angles are 90 degrees in this shape. Finally, we have xenon tetrafluoride. Yes, xenon is a noble gas, but being a big atom with lots of electrons and being that fluorine it's attached to is extremely reactive, it is able to make this molecule. This molecule also has a hybridization of sp3d2 like our last example. Therefore, the electron arrangement name is once again octahedral. But xenon tetrafluoride also has two lone pairs. Now we already discussed the fact that lone pairs take up more space, so they try to get as far apart from each other as possible. In doing so, they create a planar shape for the molecular geometry. This shape is also square, so our molecular geometry name is square planar. Now what would be the bond angle? I hope you said 90 degrees for all possibilities. So let's draw this out now. I'm going to keep the lone pairs top and bottom, and then for our square planar, we will draw one bond coming out towards us and one bond going back on either side of those lone pairs. This finishes off our chart that summarizes the basic shapes of VSEPR theory. Before ending this video, let's try an example or two to show how the shape of any molecule can be determined. Now another thing you will also need to note is that only sigma bonds are used to determine shape for VSEPR. So any double or triple bond is treated like one bonding pair of electrons. So let's try our first example. We will try nitrate, NO3 negative. Now remember, always start with your Lewis diagram, followed by counting bonding and lone pairs of electrons. Remember, total pairs of electrons will help us with hybridization, and of course that is going to lead us into the electron arrangement name. From there, we're going to look at the lone pairs of electrons to help identify what the molecular geometry name is going to be. So for NO3 minus, the Lewis diagram will be as follows. Hopefully you will get a count of 24 electrons to place for our Lewis diagram. And as I'm placing these electrons on, You will notice that when we get to the end, that this is an example where a pair of electrons from the oxygen will have to be donated as a second bond to join to the nitrogen. So here we have our Lewis diagram. Next, we're going to consider the bonding and non-bonding pairs of electrons. You will notice from the diagram that there are 3 bonded pairs of electrons, 0 lone pairs of electrons. That gives us a total of 3 pairs of electrons. Now, looking at our chart, and this is something you do have to memorize, 3 pairs of electrons always has the hybridization of sp2. And sp2 will always give you the electron arrangement shape of trigonal planar. Now you'll notice that this example also does not have any lone pairs, so that means the molecular geometry shape is also trigonal planar. Now what I want to do is a second example, but for this one I want you to pause the video and try it on your own. So try to determine the molecular geometry name of phosphorus tribromide. So pause now, and when you return, I will have an answer for you. Okay, so hopefully this is what you got for the Lewis diagram. And I hope that you noted that there are 3 bonding pairs, 1 lone pair, which gives you a total of 4 pairs of electrons. 4 pairs of electrons is always sp3 hybrid, and therefore sp3 hybrid always gives you an electron arrangement name of tetrahedral. But with the 1 lone pair of electrons, this changes the molecular geometry shape name to be trigonal pyramidal. Now, if you're not able to do this, be sure you're writing down your questions so you can ask me in our next class. And hopefully you did follow along with me and hopefully picked up the clues on how to do VSEPR naming. In our next class, you'll be given some examples to work on, and I will be there to help you out. So I will see you then.